Hi everybody, welcome back to Chem 121. We'll let the music wind down here. It's Monday. We know what that means. Time for more chemistry. This week and next week, we're going to have lots going on because you have 2 quizzes due this week. We're going to do Chapter 4, probably mostly today. Chapter 5, mostly next Monday, and then we will have done the first 5 chapters, and you'll be all set for midterms, dun dun dun, which are coming up next week. So make sure you're staying on top of the content because more assessments and stuff are going to be added, and there's a lab this week that we're going to discuss. Probably on Wednesday, just because that's what I feel like. I don't know. I don't have a good reason for it. Make sure you look at lab number 2 as well while you are doing quiz number 2, which is due tonight. Quiz number 2 has a deadline of Monday the 26th. That's the soft deadline. You do get an extra day. Remember that. Quiz number 3 is due on Wednesday, 28th. Hopefully you've already done at least one of those. You can take them out of order, that's fine. I don't care at all. With regards to labs, lab grading takes a long time. And so the reason that it takes a long time isn't because there are a ton of your labs to grade. So, like, I've actually graded this class's labs, the Chem 121 labs. But what I try to do is I try to do all the grading for all my classes and then upload it all at once, so that I know in my head who I have given stuff to, like in terms of grades and papers. Because as the number of students increases, it gets harder and harder and harder to manage in my head, like in my monkey brain, who has received what. And so I try and keep it as organized as possible. And so what that means is that once I've graded all 120 labs or 150 or whatever it is that I have, I will then upload everything to Canvas and enter all the scores. So the turnaround on that is usually going to be about a week and a half. So probably at the start of week 5, you'll get your first assignment back. And then at the start of week 7, you'll get your second one back. And then so on and so forth until we've graded them all. All right. Let's continue where we left off last week, which was talking about bonding, particularly, ionic bonding. Now, for this, you are going to need the periodic table. So hopefully I don't need to link p-table anymore. If you need it, yell at me in the chat and I'll go find the link for you. But hopefully you have that bookmarked. We're going to use that in Chapter 4 to basically skip over all of the stuff that we talked about in the end of Chapter 3. That we didn't talk about. I'm sorry, I should be more clear. So the first thing we want to do is we want to talk about how bonds happen. Now, bonds are all the result of electrons. And electrons need to be in some specific orientation around the nucleus in order for the atom to be stable or for it to be reactive. Now, on the screen, I put a bunch of red dots on certain electrons in these diagrams here. And so I've just sort of picked 3 different atoms. So I picked helium, chlorine, and potassium, and I drew their pictures. So we know the number of electrons that chlorine and potassium would have based on their atomic number. Remember, the atomic number is Z. So if chlorine is a neutral atom, it would have 17, that's a 7, 17 protons and 17 electrons, right? And here they are. So if you count these black dots, you should get 17. So 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the red ones on the outside are 7. So that's 17. And then over here, you should have 19 protons, which are in the nucleus here, and 19 electrons. So same as before, except I filled in the last guy, which would go right here, and then that one. All right. What's special about the electrons that I have highlighted in red here? So these and then this one. Well, they are on the outside. And you might think that that's not really super important, but imagine if each of these, like, rings was an onion, like, skin. So you know, everybody knows how an onion works, right? Where you peel away a layer and there's another layer of onion, and you peel away a layer and there's another layer of onion. You peel away a layer, and then they get smaller and smaller and smaller. But there's always another layer of onion, right? Electrons are sort of like onion, in the sense that there's only so much space, and so if you want to have more onion, if you want to have more electrons, you got to make a new layer. And so that's what happens, is we get layer upon layer upon layer. And there's always going to be some layer that's on the outside. The outside layer is what sees the world. So if I have an atom and another atom, and they interact with each other in such a fashion that their electrons would exchange or share or whatever, the only electrons that are going to actually get to do this are the electrons that are in the region where the atoms contact. Because they're not hard spheres, they could pass into each other, but they won't do that because electrons have charge, and that charge tends to make them want to repel. So if I have two atoms that are going real slowly next to each other, they'll go, oop, repel. But if they're going fast enough, they will bonk into each other, and the outer electrons will scramble. And the result of the scrambling is the lowest energy configuration that is possible, which results in the bond. So our outside electrons are the only ones that are far away enough from the nucleus to be the ones that get to interact. Everything else is too tightly bound to the nucleus, and you're not going to get to see those things before you see the outside electrons. We're going to call these outside electrons valence electrons. Valence electrons are the outermost electrons on an atom. There are always between 1 and 8 valence electrons. Now you might have noticed on our diagrams here, the first ring has 2 electrons, the second ring has 8, and then the third one had 8. And you might go on to think, oh, well, maybe 8 is just the magic number. And it kind of is, it kind of isn't. You can actually put more electrons in these rings, but they always fill to 8 first, and then weird stuff happens that's beyond the scope of this class. So, for our purposes, you are always going to have a number of valence electrons between 1 and 8. And the way that you count those electrons, is by using the periodic table. Now, what about the electrons that are in black here? They do have a name. That's the wrong pen. These are called core electrons. They're called core electrons because they live in the core of the electron cloud. So there are only 2 classifications of types of electrons around the nucleus. Valence electrons are on the outside, and core electrons are on the inside. Only the valence electrons participate in bonding and are thus important for us to study. We're never going to concern ourselves with core electrons because they don't participate in bonding. Do they do other interesting things? Yeah, they do. Just we don't care about them in this class. Now, if you look at the periodic table, and you'll notice that I have like the first 4 periods here, and we number the periods going left to right like this, what this tells you is the number of valence electrons in that atom. Now, if you took the time to read the end of chapter 3 in the textbook and read about electron configurations just out of curiosity, or maybe you didn't know that you weren't supposed to read that, or whatever, you might remember all this S electrons and P electrons and 1s2, 2s2, 2p6. I teach that to my engineers, but for you guys, I don't think that there's going to be a situation where the doctor rushes in and says, "Quick, nurse, tell me how many d electrons iron has." Boop, boop, boop. And then the patient dies. Like, you don't need to know about valence electrons and electron configurations. But what we learned that content for is to get these numbers. Because you can look at boron and say, oh, it has 2s2, 2p1. There are 3 electrons and n equals 2. That's great. Like, for an engineer, cool. For you guys, who gives a shit, right? Just look at the group number. Now, these numbering schemes this is the old group scheme. Now, if we go to p-table, we can look at the actual numbering scheme that is used today, which is just to number the groups from 1 to 18. So let's get this open real quick. There's p-table. Hey, that's perfect. Look at that. Okay. Now you're going to notice up here are my numbers, 1 through 18. The ones column digit tells you the number of valence electrons for the atoms we're going to be looking at, which is these two columns here. So this column and, oops, I didn't mean to click on an actual element. So these two columns right here. And then all of these columns over here, this whole block. Now what about for the middle stuff? Does this tell you anything about valence electrons? Yes and no. So valence electrons for transition metals are a little bit weird. And we aren't ever going to really do covalent bonding with transition metals. So we're not going to super care about how many valence electrons they have. We're just going to tell you the charges on those metals in the first place, if that comes up. So don't worry about valence electrons for transition metals or lanthanides or actinoids. Just the main group elements. So the first two columns and then 13 through 18. And again, you want the ones digit of the group number. So, oops, I don't want to minimize. I want to do that because minimize doesn't do anything for you. So let's write that down. So use the ones digit of the group number. That G doesn't really look like a G. All right, and that's going to be the number of valence electrons for that given atom. So we could say, I got phosphorus here, and so we say, oh, okay, well, phosphorus is in group 15, or 5A. The ones digit is 5. It has 5 valence electrons. Magnesium over here is in group 2A, or group 2 on the new normal numbering scheme. The ones digit is 2. There are 2 valence electrons. 2. Ha, ha, ha. If you are someone who has a child that watches Sesame Street, you probably laughed at that. All right. Now, why do we care about counting valence electrons? Well, depending on how many valence electrons there are, you get different outcomes in bonding. And so what we're going to first do is we're going to first learn how to count valence electrons on atoms, which we've sort of already done. And then we are going to learn how to draw that as a picture. Because we can do chemistry by shuffling around these pictures. And when we do that, we will get a better idea of how bonding is occurring. Now, there's a really smart guy. His name is Jan Lewis. And you may have heard the Lewis part of this in terms of Lewis structure or Lewis symbol. So the Lewis symbol of an atom is just a representation of the atom in a very simplistic sort of caricature. So here's how we're going to draw the Lewis symbol of any element. The first step is to write its symbol on your paper. I should get the highlighter for this. There we go. And then the second step is to draw dots per valence electron. So if you have 1 valence electron, you draw 1 dot. If you have 8, you draw 8. Now, when you have a symbol, so I'm going to write this, I'm going to just pick a symbol here. We'll do, I don't know, I'll just put X. When you put your dots in around your symbol, you just put them wherever you want to, like that, right? Now, there's only 4 sides. So our electrons are going to want to go on one of those 4 sides. Either left, up, right, or down. Furthermore, when I'm putting in my electrons, if I have a bunch of them, remember the fundamental properties of electrons. Electrons are negatively charged. If I just do this, they don't want to be next to each other, right? Because electrons would repel. So when I go and draw dots around an atom, I'm going to put 1 on each side first and foremost. And then I'll start pairing them up. So here's how I'd get to 8. 1, 2, 3, 4, 5, 6, 7, 8. And so you'd have 4 pairs of 2 if you got to 8. Otherwise, you'd have some number less than that. So that's the gist of how you draw a Lewis symbol. Let's do this with actual elements. So we're going to start with sodium. The first step for drawing any Lewis symbol is to write the symbol. There you go. That's easy enough. And then we're going to draw a dot for each valence electron. So we're going to go back to the periodic table. We're going to find sodium here. There it is. What column is it in? Well, it's in column 1. The ones digit of 1 is 1. So there must be 1 valence electron. And so we'll... Oops, that's not the right screen for me. We'll draw 1 valence electron. Boom. There you go. And that's it. That's all you have to do. Easiest thing ever. Now, what if you were doing this alongside us and you decided to do this instead? Is this okay? And the answer is yes. Totally valid. You can put the dot on any of the 4 sides you want. In fact, you might want to do that based on where you draw your Lewis structure relative to other things, because you're going to be drawing more than one atom eventually. So you can put this dot on the top, you can put it on the left, you can put it on the bottom, you can put it on the right, as long as there are the correct number of dots and you have the correct symbol. Those are the only requirements. When you get enough electrons that you have to pair them, then we add in the requirement that, oh, electrons repel, only pair them if you have to. So let's try oxygen here. So oxygen, symbol is O. Boink, there you go. That's easy now. And then I want to draw a dot for each valence electron. So back to the periodic table we go. How many valence electrons does oxygen have? I'll give you a second to think about it while I get the window open. There we go. I'll just select it. How many valence electrons does it have? Well, it's in group 16. The ones digit is 6. There are 6 valence electrons. So I'm going to add 6 dots. But remember, electrons repel. So I need to add them one side at a time. And then I'll start pairing them. And you should get something that looks like that. And so I'll do that with my little thing. There you go. Now, where do your paireds and your unpaireds go relative to each other? It totally doesn't matter. So if you do this, I'm just trying to match up the colors here. So if you did, say, that's totally good, because you put one down and then you paired them because you had to. And so those unpaired electrons could be on any 2 sides that you want to. Now, here's an example of what would be incorrect. So if I did this, for example, this would be wrong. And the reason for that is because electrons repel. So one of these pairs is going to repel and take up this empty space down at the bottom. Now, it doesn't have to be that one. It could be any one. Any pair up there should split its pair into 2 singles. All right, so your task is to draw Lewis symbols. I want you to draw them correctly. So remember, do 1 dot at a time per side, then continue adding dots as necessary until you use all the valence electrons. So you will need p-table. Go ahead and draw the Lewis symbol for each of these elements. And we'll go over the answers in about 4 minutes or so. One more minute, we'll go over the answers. Once Sarah gets her cat off the counter. Oh, speaking of cats. Say hi. Say hi. Hi. Yeah. No. Okay. Maya does not want to say hi right now. She just wants to draw valence electrons. Sorry, I got a little distracted there. For some reason, my phone had a pop-up for... I don't know. So it's like Venmo, but I guess Samsung has their own version of it. And it was at the bottom of my phone window. And I'm like, I do not want this here because I'm very particular about what is on my phone and what pops up all the time. And, like, I don't want any of the bloatware. All right, so we got carbon here. We're going to count valence electrons. So what I'm going to do here is I'm going to go like this, but that's going to get in our way. So I'm going to crop out just the ones that we want, which unfortunately that's not going to be super. Let's see, we don't need temperature and stuff up there. And then we'll just shove this in the corner here. Okay, so now we should be able to see that. So if I look at carbon, and here's carbon on my periodic table. I got to find it. There we go. Boop, there we go. So there's carbon. Carbon is in group 14. The ones digit is 4, so there should be 4 valence electrons. So I'm going to do 1, 2, 3, 4, just like that. 1 on each side. Oops, that's not what I meant to do. All right, let's find lithium. Here's lithium over here. Lithium is in group 1. It should have 1 valence electron, and there it is. No, I'm just kidding. Lithium does not come pre-programmed with its own valence electron. You do have to draw it. But that being said, be very careful that you don't accidentally... Oops, that's the wrong pen, but you know what, that's fine. Be very careful that you don't accidentally mistake the dot on the eye of lithium as an electron. So in some cases, you might want to draw this big, stupid dot. So it's like, oh, this is very obviously the electron and not this thing right here. All right, so let's look at sulfur. I keep hitting my phone with my finger when I reach for the mouse, and then things are appearing on it. Sulfur. There we go. Ah, that's the wrong window. That's the right window. Where is sulfur? It's in column 16. Group 16, that's the one's digit is 6, so it should have 6 valence electrons. We're going to do 1 around each side, And then we're going to just pair any two. I'm going to pick these two. Just to be contrarian, I'm going to go backward. Totally fine. You can do it in any order you want. Let's look at chlorine. Chlorine's over here. Boop. Chlorine has 7 valence electrons because it's in group 17. So 1, 2, 3, 4, 5, 6, 7. There you go. That single can be wherever it wants. All right, here's aluminum. We'll highlight aluminum here. Boop. Oops, I didn't mean to actually highlight the text there. There are 3 valence electrons around aluminum because it's in group 13. The 1's digit is 3. There you go. And then I ran out of space for xenon, so we'll put him over here. Where's xenon? Boop, there it is. Xenon's in group 18. 1's digit is 8. That's 8 valence electrons. So we'll do that. 1, 2, 3, 4, 5, 6, 7, 8. You'll notice that there's only one way to draw 8. And if you had to do 9, well, there wouldn't be anywhere to put it other than to make like a pair of 3 or a set of 3. Fortunately, we only have to go up to 8 because 18 is the last group on the periodic table. All right, that's how you draw Lewis symbols. Let me know if you have any questions. In the next section, what we're going to start doing is we're going to start doing bonds. Oh, I can put the homework practice up too. Here you go. We're going to start doing bonds with these symbols by reaching a very specific condition. You can't see the homework practice because this thing is in the way. Let me just do that real quick for when we need it later. We're going to try and reach a specific condition to achieve bonding. In that condition, I wonder if it has something to do with the number of valence electrons. Oh, no wonder I can't see the cursor. I have the pen pointed in the wrong direction. What number is octet? I mean, if you think of octopus, or heaven forbid, octuplets, you know that octet means 8. So there must be something special about 8. And it turns out there is. For all the atoms that we're going to be examining, the goal is to reach 8 valence electrons. If they don't have 8 valence electrons to start with, which most atoms don't because they're not in group 18, then they will try to get to 8 valence electrons in any way that they can. You can think of it as electron Hunger Games. Only the noble gases have an octet. Now, what are the consequences of having an octet? It turns out that some elements don't really react with anything. The noble gases, for instance, are totally inert. Like all nobility, they sit on their asses and do nothing. And that's because they don't have to. They have everything they want. They have all the electrons. All 8 of them. So for elements like krypton or neon or argon, there's really no incentive to react because reactions would require us to change electrons around. And they don't need to do that because they already have 8. So the goal for atoms is to get to 8 valence electrons. Now, that will turn all other atoms into ions. Only the noble gases get to remain neutral when they do this. So if an atom or ion has 8 valence electrons, it becomes more stable than it was previously. Now, I should probably put that word in here, because that's kind of a critical word. It doesn't become absolutely stable, it just becomes more stable. But I leave it out so we can have this discussion. Chemistry is very relative. Even noble gases under very weird circumstances will react. So it's strange to talk about like absolutes in chemistry because there aren't any. All of the reactions we're going to study are giant gradients. Nothing is black and white in chemistry. So everything is relative. Just keep that in mind that whenever I say something like it is stable, what I mean is relative to how it was before. And I mean that in virtually every case. It is acidic, or it is strong, or it is stable, or whatever I say. Now, we're going to look at various ions that form when we add or remove electrons to get to our octet. Because adding or changing the number of electrons will change the charge that is present, and that leads to interesting things. So that's the octet rule. The octet rule is if you have 8 valence electrons, you are stable relative to what you had before. If you don't have 8 electrons, then you need to get 8 electrons by either taking from someone else or giving yours away. Now, how would you get to 8 valence electrons by giving away electrons? Well, it has to do with going back to that diagram that we showed before, and we will go back to that in just a second. So let's start with the obvious method of getting to an octet. Oh, I have like 6 or 5 or 7 or something. I need electrons, so I will take them. Elements on the right side of the periodic table are very close to having an octet, but they're not quite there. So I'm going to show you that right here. So elements over in these groups, 15, 16, 17, they're so close. They can taste it. They just have to get 1 more electron, or 2 or 3 in these cases. They're very close. So what we need to do is we just simply give those elements electrons. So here's oxygen. I'm going to give it 2 electrons. Here they are. I've colored them a different color, so you can see which electrons I gave them, but functionally all electrons are identical. Here is our new oxygen, but now the number of valence electrons has changed, but also the total number of electrons has changed. Be aware that we are counting valence electrons here and not total electrons here, because if I was counting the total number of electrons, I would get 8, because oxygen is element number 8. But it has 6 valence electrons, because it's in group 16. Now, because we added 2 electrons, and electrons are negative, we change the charge. O2 minus has a charge of -2 because we added 2 extra negative electrons. All right. You can do this strategy for any element in these groups on the right side of the table, so groups 15 through 17. Why not groups 14 and 13? Well, there's something weird going on with group 14, which we'll briefly mention. And then group 13 actually is closer to going the other direction, strangely enough. So if we go like this, and now we consider elements that are in the left side of the periodic table, they have 1 or 2 valence electrons here. Now, gaining 6 or 7 electrons is a thing that could happen, but it's not very likely, because I would have to stick 7 extra electrons around lithium, for example, and electrons repel each other, and lithium doesn't have enough protons to pull all those in. So, how the heck do we get an octet? And what we're going to do is we're going to go back to this picture, all the way back at where we started the lecture today. Here we go. So let's look at potassium here. And what I'm going to do is I'm going to go like this. I'm going to take the highlighter, and I'm going to highlight the valence electrons. See here, my potassium is 1 valence electron. And what I'm going to do now is I'm going to do this. Well, I would if I could select the right color. Boop. I'm going to remove it. How many valence electrons are there now? And you might look at that and say, well, there's 0. How does that get me to an octet? And then I'm going to say, well, if there's 0 valence electrons, then that layer doesn't exist, right? How many valence electrons are there actually? There they are. It's now the next layer down. So if you can get to 0, then the next layer down becomes the octet. Pretty sneaky. And that's how it works. So if you can delete your electrons by pawning them off to somebody else who wants them, potassium has 1 valence electron. It just goes, gets rid of it. Don't need it anymore. Goodbye. Then it will have 8 valence electrons because the next layer down becomes the octet. Now, why does this work? And the answer is, well, let's look at the periodic table and how the periodic table works. Where's potassium on the periodic table? It's over here. If I take away 1 electron, what does it look like? Well, it would have 18 electrons, which would look like this, and that's a noble gas. Woohoo! So that's why this works. Now, I'm cherry picking my answers. That strategy of, oh, can I make the number of electrons look like a noble gas, works for most of the elements, but not all of them. For now, we're just going to count the number of valence electrons based on what group it's in, and then add or subtract electrons to get to 8. Let me scroll back to where we were here. There we go. So here's my sodium. I'm going to abandon its electron. Boop. I'm just going to get rid of it. It now has 0 valence electrons, but then the next layer down becomes the octet. So your goal as an atom is to either get 8 valence electrons or get to 0. There are weird exceptions to this. Lithium, for example, lithium can't remove electrons to get to an octet because it has fewer than 8 to begin with. However, helium is a noble gas, so if early elements can look like helium, that counts. So we're going to see later on that hydrogen is a notorious offender of breaking the octet rule because it can't get to 8. It only has 1 electron anyway. So it creates its own rule, the duet rule. So the duet rule is like the octet rule. We're going to work with lithium very, very rarely anyway, in terms of like ionic compounds. So don't worry about it too much. All right, so what I want you to do now is I'm going to give you a collection of ions here that I've just sort of randomly put charges with symbols. And so what I want you to do, and I'm going to show you how to do this for the first one, so you have an example here. First, draw the Lewis symbol for the species that you see. And I actually do want to use the filter pen. So I'm going to draw this K plus here. So I'm going to draw potassium with its valence electron. Then I need to make it K plus. Oops, that color is way too strong. Sorry. Then I need to make it K plus. In order to make something plus, I would have to remove an electron. So I go like this. Boop. And then once you have done that, check if that is an octet. If it is, then that is the ion that should form. But if you do something like, say, like instead of K plus, let's suppose that we had to do K2 plus. I'll just write it again. If I try to do K2 plus, I would need to take an extra electron away, but there are no extra electrons to take, so I can't actually do that without digging into the next layer down, which would mean that K2 plus does not make an octet. Okay, some of these are going to require you to dig further down than the octet to get the result that is shown. For instance, calcium 4 plus does that. So what I want you to tell me is which of these resemble an octet. So go through and draw the Lewis structures in for each time I either remove electrons with the plus or add electrons with the minus. Okay? We'll go over the answers in about 4 or 5 minutes. If you have any questions about these, let me know. One more minute, we'll go over the answers. All right. So for these, I'm not going to flash the periodic table on the screen like this. I'm going to assume that you can look at it and can follow along. So let's look at calcium 4+ here. So here's my calcium. Let me just draw that with the normal size pen. There we go. And then I'm going to draw its valence electrons in here. And I'm going to do those in this color here. Okay, so calcium is in group 2. So it should have 2 valence electrons. Now I need to make it +4, which means I need to cross out 4 of them. But there were only 2 to begin with. So could calcium 4+ follow the octet rule? And the answer is no. Calcium +4 is not the ion we would expect to follow the octet rule. Now, what ion would follow the octet rule? It would be calcium +2 if we just got rid of the 2 that were there. Let's look at Br-. Bromine has 7 valence electrons because it's in group 17. So 1, 2, 3, 4, 5, 6, 7. Now we want to make it bromine with a minus charge on it. That means I need to add an electron. So I'm going to add an electron, and we're going to do it in a darker color. There we go. Did I reach an octet? And I did. So Br- should form. How about N2-? Let's look at that. So nitrogen. Nitrogen is in group 5, or 15, sorry. So it's 5 valence electrons. So 1, 2, 3, 4, 5. Now I want to make it 2-. So I'm going to add 2 electrons to make it 2-. Did I reach the octet? Oh, missing a spot, so no. N2- is not what would form. What would form? Well, if I added an extra electron, that would be N3-. That would form. How about aluminum? Aluminum has 3 valence electrons because it's in group 13. There they are. Now I want to make it 3+. So I got to get rid of 3 electrons. 1, 2, 3. To make it 3+. I realize I didn't put this charge over here, but that's okay. Did I land on the octet? Did I get rid of all the valence electrons? That's an octet, so this one is what forms, aluminum 3+. And then finally, phosphorus. Phosphorus has how many valence electrons? Well, it's in group 15. So that means it has 5. And I want to 3- it. I'm going to give it 3 extra electrons. So let's do that. 1, 2, 3. Did I achieve the octet? Yes, I did. All right, so that's kind of a weird little assignment. But now that you've seen it, hopefully you understand what the point of it is. What things land on octets and what don't? Not every combination of atom and electrons will land on an octet. all of the ones that did, these right here, so we'll circle those over here. So that's this guy. Oh, also K+. These two. They all land on an octet, and anything with an octet is expected to form. So what that means is that when you put potassium into a situation where it can gain or lose electrons, it will become K+, because it has an octet. So all the potassium that you eat in your diet is K+, because it has exchanged its electron away. It now exists as K+. This is why potassium is safe to eat. As opposed to when I've shown you videos of like, wait a second, potassium and water equals explosions. Yeah, that's potassium atom. But what you eat is stable. It's potassium in the ion form. It has an octet. All right. Oops. I bumped the mouse and for some reason it went backwards. All right. When we get back from the break here, we're going to talk about ions in a little bit more detail. But it is 3:30, so we're going to put the timer on here. That's the wrong style of timer. Hold on. I was playing something that only needed hours and minutes, so I want Raz's timer here. Here we go. And we'll start the clock. Oops, that's not how you start the clock. That's how you start the clock. I hit the wrong button. And let me get the music going again. And I'll see you in 10 minutes. I like when I land exactly on 10. Alright. Wind the music down. I really like the soundtrack to Endless Space 2. That was a fun game. I should go back and play that. Alright, welcome back. Let's talk about forming ions. So, a lot of this part is going to more or less be a rehash of the previous part, because now that we've learned how to construct ions, and we know which ones are stable, we should be able to predict them. So, first, let's define what an ion is. An ion is any particle that has a different number of protons and electrons. Now, if you're gaining electrons, you become an anion, because the charge is becoming more negative, and we define an anion as anything with more electrons than protons. If you get rid of your electrons, you become a cation. And cations are, by definition, any particles that have more protons than electrons. Or we should just keep it consistent. Fewer electrons than protons. Now, how do you keep those two things straight? I don't know if we've done this little mnemonic, so I write the word cation, and then if you put the plus in where the T should be, it still looks like the word cation. So that's how you know which one's the positive one. Now, there is another mnemonic out there, and I'm going to do this for my colleague who does this for his students. You can't see me clawing at the screen like one of those lucky cat statues that you often see set out for good luck. Like, they have the paw that wags or whatever. It's those little statues. But I'm doing that, and I'm going to say, cats have paws, positive. And that's how you remember cation, pause, positive. I mean, it's stupid, but whatever helps you remember. And then anion is the other one. On the board here is just a list of electrons versus protons and then their overall charge. And you can see that as I add electrons, the charge becomes more negative. And as I remove electrons, the charge becomes more positive. The number of protons never changes when we do any of these add or remove electrons, because it's hard to play with the nucleus. You can't really do much to it. Alright, so let's do some examples here. Write the symbol for sodium if you lose one electron. Okay, that's easy enough. This isn't just draw the Lewis structure, although we're going to do that later. There's my sodium atom. If I lose an electron, that's this charge, right? So I would write Na with a plus. Maybe your A would be a little more looking like an A. Now my A looks like it has a toupee. Oops. And now all the text is gone. There you go. That's what you should get. All right, let's do a different one. Nitrogen gaining 3 electrons. Well, nitrogen's symbol is N. And if I'm going to give it 3 electrons, I would put a 3. Electrons are negative. So that's what I get. That's easy enough, right? All right. So I want you to do that with these descriptions here. So I'm going to give you a few minutes to do that. I actually have to go use the restroom. So we'll go over the answers when I get back. See you in a bit. All right, I'm back. Sorry about that. What is it with cats and when you use the restroom? Like, that's when the cat decides, like, it's time to say hello. I'm going to give one more minute, and then we'll go over the answers. All right, let's go over the answers. But first, we'll say hi to Maya, who's followed me. Say hi. Say hi. There you go. Yeah, I always like to joke with Maya that, like, because I have like this little box in my bathroom. It's like a something that you would carry, just like, I don't know what to call it other than just like a bin. It's like it's rectangular and there's like stuff in it for like cleaning supplies and things like that, because under the sink is their litter box. And so I don't really have space to put all the cleaning supplies. So they sit in this bin with a lid on it. Well, Maya likes to jump up on that bin, which is conveniently right in front of the toilet. And she rolls around like the cutest thing. And it's like, Maya, I'm trying to use the bathroom here. Why are you bugging me? I don't watch her go to the bathroom. Uh like, that's gross. But nope. Anytime the human is present. All right, so we're gonna write these descriptions here. So copper, we're gonna get rid of 2 of its electrons, so we're gonna write that. Sulfur, we're gonna give it 2 electrons, so we'll do that. Hydrogen loses its electron. There you go. Platinum loses 4 electrons, and chlorine gains an electron. There you go. That's easy enough to write ions based on description. So the point of that exercise is for you to understand that gaining electrons means negative and losing electrons means positive in terms of charge. And I know, like, intuitively you want to say, oh, well, losing something should be negative, right? But that's the opposite of what's happening, because we're subtracting a negative thing to begin with. Number first, then sign, yeah. Honestly, you can do it in either order. The correct convention is to do number first, then sign. However, on Canvas, if a question asks you, like, type in the charge, the directions will say number first, then sign, and if you don't do that, it'll mark it wrong. So normally I'd be like, whatever, but on Canvas, I have to program it to accept certain answers, and I can't do every possibility, unfortunately. So do number first, then sign, no spaces, and you're good to go. And then also do the homework practice. That's important too. All right, what do we got next? Now we're going to show how to make ions in the first place. You got it, no problem. So now we've already talked about the theory behind ions. Oh, I get rid of an electron. Oh, I accept an electron. How does that actually happen? Like, in real space? Like, what's the mechanism by which this happens? So we're going to show first that ions always satisfy the octet rule on paper when they want to undergo a reaction, and then we're going to show you the reaction. So our goal is to make the ion that follows the octet rule. whatever that ion is. And you'll notice that there's always only one possibility. So for sodium has one valence electron. My only possibility to follow the octet rule is to get rid of that one electron. I got rid of one electron, so this is now what I have. This is the ion that forms. What if I had calcium? Well, calcium has 2 valence electrons. I could get rid of its 2. This is the ion that forms. What if I had, like, chlorine? Chlorine has 7, right? I want to get to the octet, so I need to gain an electron. Ooh, that's not a color that you can really see. We'll do purple. There we go. I'm going to gain an electron, which means I do this, and this is the ion that forms. You'll notice that I'm circling the charges. That's not something that is required for you to do. I circle charges just to make it clear that that's not a stray mark or something like that. Because like a minus can look kind of funny by itself. All right. So let's do some more. I want you to predict what ion forms for oxygen, despite the fact that we've done like 3 examples with oxygen already. So draw the Lewis symbol for oxygen. And then fill in the valence electrons that are missing to get to the octet, or take them away if you have to. And then write the charge that represents what you just did. And then type the result that you got into the chat. All right, so you have the right answer. Let's go over why that is. So here's my oxygen. Oh, it's in purple now. That's fine. Oxygen has 6 valence electrons because it's in group 16. And then I'll just go to this color. I'm going to add electrons to get to its octet. I had to add 2, so this is its charge. This is the ion that forms. Oops. There you go. All right. Let's do that with all these things. So now what I'm going to do is I'm just going to give you the straight up element off the periodic table, and you have to do all the work to get to the end now. So what ion would you expect barium to form, or aluminum, or phosphorus, or etc.? Okay. Now, for one of them, you might go, oh, well, no ion is expected to form at all because it's already got an octet. So then the expected ion, quote unquote, would just be the symbol. You just write the element by itself as you normally would. Okay? Go ahead and do those. We'll go over the answers in about 4 or 5 minutes. All right, one more minute. We'll go over the answers. All right, let's go over the answers here. So again, I'm going to be referring to p-table. So if you are working along with me, make sure that you have that handy. So barium is in group 2. So when I draw its valence electrons, I would draw two. Oh, you know what? Let's do a different color here. Because that black looks like the little mark or the little bullet point that I have here. So I'm going to do 1, 2. In order to make an ion, I would have to get rid of those two. So I would form this ion. For aluminum, same situation, but aluminum's in group 13, which means it has 3 valence electrons. We'll get rid of those 3. There you go. Phosphorus is in group 15, so it's going to have 5 valence electrons, which means I got to change colors here. So I'm going to add 3 more to get this. Selenium is in group 16, so it has 6 valence electrons. I don't know what happened with this one. There we go. So we're going to add 2 to it to get to an octet. There you go. Krypton's already got 8 valence electrons, so it doesn't need to do anything. So when you get to here, you're like, oh, it's not going to ionize. You're just going to keep it the same. And then finally for astatine, astatine's radioactive, but you could potentially do chemistry with it because it would have 7 valence electrons. And then if you gave it another one quick enough before it decayed, then you would get astatine with a minus charge. There you go. All right. I think that we know how to make ions. So let's see how this actually carries out in practice. But first, write down the homework practice before I go to the next slide. So I'll give you a second to do that while I drink more cranberry lime seltzer water here. All right. What time is it? I don't know how many more sections we can do today. So I know this one's short because we're going to watch a video. So let me get the video going real quick here. So what I'm going to show you is how an ionic bond is formed from elements that are neutral. So what we're going to do is we're going to do this reaction. We're going to react. I just got rid of the pen, but oops. We're going to react sodium and chlorine gas together and see what happens. Or in other words, I'm going to react sodium, which looks like this, and chlorine, which looks like that. Will something happen between these to form the ionic compound NaCl? Because this is table salt. We already know that ions attract to each other if they are already charged, but what if I have something that isn't an ion yet? How do I make it become an ionic compound? Because there must be some intermediate step, right? So let's watch this video and show how that happens. Okay, first of all, I have the right video, so that's important. Trying to put it in the window that I already have captured, but it's not actually working super well. Let's see here. Got this one, and then we'll go like that, and then we'll put it here. So now I should just be able to go boop. Okay, that did kind of work. All right. This is Lonnie. Lonnie teaches at UC Berkeley, I believe. I should just make it smaller. There we go. Okay. So what Lonnie's going to do is he's going to do the reaction of sodium metal with chlorine. And I'm actually going to just talk over the audio. I think there are closed captions to this, and I'll just turn them off. Yeah, I've already turned them off. Okay. What Lonnie has here is there's this container right here. I'm going to hit pause real quick. You can kind of see, because his lab coat is behind it, right here where the mouse cursor is. See how it's kind of yellow? Kind of like his lab coat would be stained or something like that. It's actually colored by the gas here. This is chlorine gas. Chlorine gas is this pale yellow gas. It's super, super toxic. And Lonnie isn't wearing a respirator of any sort, so how the heck is he okay? Well, so the gas goes through the tube into this container, and then if any opening, it can go out. But it's over this very, very strong vent shaft. And so this is designed for colleges that have large auditorium-type lecture halls. There's this giant vent with a fan that just pulls down, and so any fumes or anything like that are pulled straight into the vent and don't disperse into the air, so he's at no risk. The other stuff that he has present, he has a Bunsen burner and a face shield. And in this jar over here is some sodium metal stored under oil. And right next to this is some hexane to wash off that oil when he cuts the piece of metal for the experiment. So he's going to take the chlorine gas out first and then close the container so that it doesn't escape, because the less there is in there, the less the reaction will go. All right, we'll put that away. And then he's going to cut a small sample of sodium. Now, sodium is a metal, and metals are very, very, very easy to cut, it turns out. Not all metals, but as you go further and further to the left on the periodic table, it gets very easy to cut those metals. They're very soft. So now that the metal is rinsed off in hexane, there shouldn't be any oil on it. He's going to put it in this scoop. And he's going to heat the scoop. And the purpose of heating the scoop is just so that the metal is hot enough that it kind of starts to melt. And that'll facilitate the reaction, because a hot starting material will react much more quickly than a cold one. And then once the reaction starts, this reaction will generate heat on its own. All right, so in it goes. And the reaction should be instant. It'll happen very quickly. There we go. Now you can see the gaseous sodium chloride being expelled out through the little hole where the ladle is, but it gets sucked right down the ventilation duct. And so what's inside that chamber right now is gaseous table salt. That's how hot it is, and you're going to see how hot this is when he pulls out the ladle, because the ladle's going to be red hot. So all of the sodium has now reacted with all the chlorine. There's the ladle. You can see it's red hot. He's going to put it on that for it to cool, because you don't want to manipulate that while it's red hot. You'll scorch yourself, 3rd-degree burn. And when this settles inside, what will eventually form is this, which he has right here on the dish here. This is table salt. And you can actually prepare table salt in this manner and then eat it. Now, it looks a little bit dirty in here and a little dingy, but that's probably just because of either residual chlorine gas or something. I don't know. But you could see down at the bottom that white table salt is starting to solidify. Lonnie, why do you have an egg? Lonnie, this is a laboratory. Why are you eating in the lab? Lonnie, I know it's your lab, but oh. Don't do this at home. Don't enjoy eggs with table salt that you made at home. Alright. Yeah, definitely don't eat in the lab. That would be bad. Alright, so something must have happened here. That's the moral of the story, is that something with these two species must have happened. And we've been talking about octets all day, so somewhere along the way we must have made octets, because that's how substances become stable. Table salt is these two ions. It's sodium plus, which we have already said is stable, and then chlorine minus, which I'm just going to fill in all the dots here for chlorine minus. That's stable. So how do I get from this to this? Now you might be looking at the highlighted thing and going, oh, I know the answer, and it's definitely this, right? So we're going to do this process. This is called electron transfer. Electron transfer occurs when one element wants to abandon its electron and another element wants to take the electron. We always transfer an electron from one atom to another. You can't put electrons in a bottle. There's no like bottled electrons that you could just feed to stuff or collect electrons into. You can only ever transfer from one object to another because things tend to want to be neutral. So if I have my atoms like this and I move my electrons in this manner, I'm going to make my sodium give up its electron, but that electron is going to go over to chlorine. If I do that, I end up in this situation. Sodium now has an octet, and chlorine now has an octet, and they have opposite charges. So now I can form my ionic compound. This is how ionic compounds form. To make an ionic bond, we have to first make the ions. To make the ions, we first do electron transfer. Now, you are not restricted to one electron transfer. You can move as many electrons as you need to. Some elements need to move 2. For example, calcium would need to move 2. And you can move them to different elements. For instance, later on we're going to talk about different compounds. We're going to stick to binary compounds in this class where there's only one metal and one non-metal element. But you can just move them to wherever you want to. If you have multiple copies of atoms that you need to give electrons to, you give it to all of them. We're going to see that in action in just a second. This just says everything that I just said. All right, so I'm going to do an example here. I'm going to pick this one for my example, just to show you what's going on here. So I'm going to write magnesium, and I'm going to write chlorine. And you're going to notice that they're offset a little bit on purpose here. That's not me being bad at drawing. There are plenty of other times I'll be bad at drawing. All right, so I've drawn the valence electrons for each of these. So we know that magnesium is going to become +2, and we know that chlorine is going to become -1. But what I need to do is I need to actually move my electrons around. So I'm going to do that. So the first move that I'm going to do is I'm going to move this electron right here. And then this atom has its octet. Now there's an issue here. I don't have anywhere to put this one. So this atom does not have its octet. So what I need to do is, if I ever hit a situation where I don't have a place to put an electron, we'll just find another atom to stick it on. Atoms are tiny and there's tons of them. So the odds of me finding another atom out there that needs an electron, 100%. We will always find it. Okay. Now that I have a second copy of this, I'll just take this electron and put it here. That gives this its octet and a negative charge. Now this has an octet because it got rid of its 2 electrons. everything has an octet. So let's write the ions that have formed now. So I made magnesium 2+, like we said, and then I've made Cl- and Cl-. What's the compound that forms? Well, I'm going to combine all the things that we made together. And their charges cancel out. So 2+ and these negatives sum to no charge. So I won't write a charge. There's the ionic compound. So that's how we got NaCl. We don't write Na plus Cl- together. We just write NaCl because all the charges neutralize, right? You can do that with any combination of metal and nonmetal that you would like to. So I'm going to have you do it with these 4 examples here. So tell me the product of KBr, or KNBr, I should say, calcium and oxygen, sodium and nitrogen, and aluminum and oxygen. Some of these you're going to have to put down a lot of extra atoms to satisfy everyone's octet rule. Keep doing it and you will eventually get to the goal. And then type the formula you get into the chat. There will always be one formula for an ionic compound. There's never a possibility of a second formula. There's always only one correct answer. So find that correct answer, and we'll go over the answers in just a bit. We're going to run out of time, so 1 or 2 more minutes, and then I'll go over the answers with you. All right, let's go over the answers. We finally get to use this today. Whee. We'll just do that. That's fine. Oops, that's not fine. Sorry. Sometimes when I open Photoshop, or unminimize it, I guess I should say, I get weird display errors. So I have to fiddle around with it until it works. I gotta move this so I can. There we go. All right, so we're gonna do KBR. So here's potassium. I have the selection tool selected. No pixels were selected. That's because I didn't try to select any. There we go. So we got potassium and bromine. Potassium has 1 valence electron. Bromine has 7. And in order to get to my octet, I need to get rid of this 1, and bromine also needs 1. So there we go. That's easy enough. We form K plus and Br minus. And the ionic compound that we would make is KBr. All right, let's do the same thing with calcium, which has 2 valence electrons, and oxygen, which has 6. So again, I need to move my electrons off of calcium and onto oxygens. So I could pair these two, and I could pair these two. Now I have 0 over here, and I have 8 on my oxygen because I would put 1 at each of those spots. That means that calcium is now 2 plus. Oxygen is now 2 minus. Now I can make my ionic compound, calcium oxide. How do I know what the formula is? Well, I have 1 potassium ion, 1 bromine or bromide ion, so 1 and 1. There you go. I have 1 and 1, so 1 and 1. There you go. So whatever you write down is whatever's going to go in the formula. Now you can also look at it from the perspective of charges. Do the charges balance to 0? If so, that's the formula. Let's show a little bit of that with this. So for instance, here's my sodium and here's my nitrogen. Nitrogen has 5. And that one looks pretty bad, so I'll redraw it. There we go. Let's suppose that I just passed one of these over here. This sodium would fulfill its octet, but this nitrogen wouldn't. So what I need to do now is get more sodium. But let's suppose I just went down and wrote what ions I would be forming anyway. So we know that nitrogen should be that. If we combine these two things together, you would get this. The charges don't cancel out, so this is not the right answer. Instead, let's just add more sodiums here. So I need to pair another sodium with this electron over here. So this gets moved. That sodium now is an octet as well, but I still have an unpaired electron here. I've got something here and I've got something here. But what's the deal here? I got to get one more, so we'll get another sodium. And we'll move its electron right there. So now everything has an octet. So I can now write down what I got. So I got this down here. So I got sodium plus, sodium plus, sodium plus. We have the Batman song over here. Na 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 na. Na 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 na. And then what's the formula? Well, I got 3 sodium and 1 nitrogen. That's the ionic compound that I made. And then finally for aluminum and oxygen, we got to come over here to do this one because it takes some time here. So aluminum, 3 valence electrons. Oxygen has 6. I'm not going to change colors with the pen because this is just going to take a while. But you can see I'm pointing these at blank spaces to fill octets. But I have this extra electron over here. What do? Well, I need to get another oxygen. So we'll put that right there. So now this aluminum's good. But now I have this extra blank spot that I need to fill in right there. So we'll get another aluminum. All right, this oxygen's good. But now I have 2 more of these to... When does it end? And the answer is it ends right here. Because now I have 2 spaces and 2 electrons to fill those spaces. So this is good and this is good. And so that's how I get the compound aluminum oxide. Because I had 2 aluminums up here. Oops, I hit the wrong thing. 1, 2. And 1, 2, 3 oxygens were needed to balance out all these pictures. Everyone has an octet. Everyone makes an ion. We make an ionic compound. All the charges balance to 0. Alright, that's all I got for today. We are out of time. I sort of ran over the time limit. So, if I could find the outro music, because I never remember to get this out when I need it. There you go, that's all I got. So, I will catch you all tomorrow, or not tomorrow, Wednesday actually, for this class. I'll see you all on Wednesday. Make sure that you get quiz number 2 done tonight. Last call is tomorrow. Quiz number 3 is coming up on Wednesday. See you then.